Here are some fun facts concerning cumulative distribution functions. First of all, since f of x is a probability, recall from the previous slide that capital F of little x is the probability that the random variable capital X is less than or equal to little x. Since it is a probability, it has to obey the probability axioms and their spin-offs, and because of that, f of x has to lie between 0 and 1 inclusive. Second of all, f of x is a non-decreasing function of x. That is, for a less than b, f of a is less than or equal to f of b. Third, the limit as x goes to negative infinity of f of x equals 0. Fourth, the limit as x goes to infinity of f of x equals 1. I think there is enough room on this slide to squeeze in a quick picture of a cumulative distribution function. Now, we know that it has to lie between 0 and 1, so you can put those in on the vertical axis. And let's start out with an example of a discrete random variable. And more specifically, what I'm going to do is I'm going to assume that the discrete random variable can only take on these three particular values in its support. So to start out, the CDF, which is the probability x is less than or equal to x, if you put in any x value to the left of that first mass value, you're going to get a 0. So this thing starts out at 0. And then what happens is there is an open circle there, and it is closed on this end. How come? Because the probability that x is less than or equal to that first mass value will just be the probability mass function at that point, and that's the size of this jump. So it will stay constant between mass values. Then at this point right here, maybe there's a big jump. Maybe it jumps way up to here, and then it stays constant between mass values. Again, an open circle, and then finally it makes it up to 1, and it stays at 1 forever. So that's kind of a generic version of what a probability a cumulative distribution function would look like for a discrete random variable. Now, in the second case, where you have a continuous random variable, here's x, here's capital F of x. Now remember, again, this is the case of a continuous random variable. And once again, you can label your axes going from 0 to 1, your vertical axes, because it's a probability. And let's say the beginning of the support is right here. It doesn't go from negative infinity to infinity. Some distributions do. But let's just begin the support right here and end it right here. Well, your CDF will be 0 up to the beginning of the support, and then it will have some type of shape in here between the beginning of the support and the end of the support. Eventually it will make it up to 1, and it will stay at 1 thereafter. And that's kind of a generic version of what the CDF looks like for a continuous random variable. The next fact about CDFs is the probability that a is less than x is less than or equal to b is f of b minus f of a. And the reason that is true is f of b is the probability x is less than or equal to b. That takes care of this portion right here. And then you want to subtract out the probability x is less than or equal to a. The random variables x and y are identically distributed if and only if f sub x of x is equal to f sub y of x for all values x. Now notice there's two random variables running around here, namely x and y, and because of that I use the subscript x and the subscript y, both uppercase, to denote the difference between the two of them. The upshot with this is if the random variables are identically distributed, their CDFs are the same. If their CDFs are the same, then the random variables are identically distributed. There are three fields, namely actuarial science, biostatistics, and reliability, and these three fields all comprise something known as survival analysis. Actuaries, of course, are interested in the lifetimes of people or buildings or, say, cars, because those things need to be insured. Biostatisticians look at the lifetime of, say, a laboratory rat, or maybe they're interested in how long a particular cancer persists in a patient. And reliability engineers tend to be concerned with lifetimes of light bulbs and complex systems such as satellites. The related survivor function, and that is S of x, is the probability x is greater than or equal to x. And by the way, some authors write this as the probability x is strictly greater than x. Notice how that is related to the CDF up top. They tend to use that more frequently than the cumulative distribution function. Finally, the last point here is if x is a discrete random variable, then f of x is a right continuous step function, and that's what we have right here in our sort of generic cumulative distribution function for a discrete random variable.